Okay, so let's have a sample problem on a design of a rectangular concrete beam. A propped cantilever beam shown is made of reinforced concrete having a width of 290 millimeters and overall depth of 490 millimeters. The beam is loaded with uniform dead load of 35 kilonewtons per meter. That is including its own weight. And a uniform live load of 55 kilonewtons per meter. Given yung FC prime, 24 MPa, the yield strength of the steel, 415 MPa. We have the concrete cover to the centroid of the bars. The questions are actually based on the maximum positive bending or the positive moment, as we can see. That's why the cross-section here given is yung AS natin is located below. Okay? As we remember, positive bending, yung reinforced natin dapat is nasa ilalim. Negative bending, yung reinforcement natin nasa itaas. Okay? So, let's start for number 1. Calculate the balance steel ratio. Okay, so as you remember, we derived the formula of the balance steel ratio of a rectangular concrete beam. Okay, so let's have this muna. The concrete cover to the centroid of the bars. So that is 60 millimeters. That means our effective depth here is just 490 minus 60. And that is 430 millimeters. Okay, 490 minus 60. Now, let's have the balance steel ratio. That is 0.85 FC prime beta 1 times 600 Fy quantity 600 plus Fy. Okay, that one. Now, ano yung beta 1 natin dito? Okay, beta 1 is given by this code. This is NSCP 2015 in this table. Okay, so as we can see, beta 1 is based sa value ng ating FC prime. Okay, since our FC prime here is 24 MPa, nag-fall siya sa region na ito. Okay, sa first region. FC prime is greater than 17 MPa. Okay, but that is lesser than 28 MPa. That means our beta 1 should be 0.85. Take note lang, no, that this is from the actual NSCP 2015. Okay, so may typo error dito. Dapat at this region, dapat 0.85 minus this quantity. Walang nalagay na minus dyan. Okay, so take note of that na lang. Okay, direct substitution. And we have this row balance. In case hindi ito rectangular beam, so hindi natin ito magagamit na formula. Okay, for number 2, calculate the required steel ratio. And number 3, calculate the required number of tension bars. Okay, so actually, prerequisite sila, or kumbaga yung number 3, first kukunin pa natin steel ratio, then makukuha natin AS, then makukuha natin yung number of bars. So how will we start? So take note, we need to design the bottom portion of the beam or the location of the maximum positive moment. So as we can see in the beam, we should calculate the positive moment here. But take note that this is a indeterminate beam. So, may halong theory of structures yung problem na ito. Okay, so, just recall lang. So, here, I will do the 3-moment equation. Okay? Alam nyo maraming methods in calculating the indeterminate beams. Okay, so here, I will do the 3-moment equation. Okay, so, if this is a prop beam, I will extend this one with. Okay, so for step 1, no, in designing, dapat makuha natin yung MU. And of course, para makuha yung MU, dadaan tayo dito sa theory of structures. Okay, so let's calculate na lang muna yung ultimate or the required or the factored load. Okay, given by this combination. So we have the dead load and we have the live load and we have this W. Next, after we got this, ito yung gagamitin natin dito para makuha yung factored moment. Positive yung kukunin natin. Okay? Now, extend ko yan dyan. Gagamitin ko yung 3-moment equation. I will call this point O and that is LO. Now, take note, in 3-moment equation, we need to use at least 3 points of the beam. So, gagamitin kong 3 points is that one, this one, and that one. Okay? And ito yung ma-recreate nating equation. M1 here is the moment at point 1. Ito yung point 1 ko. L1, that will be this LO. M2, that will be my moment at A. Okay, then L1, then L2, this is the 6 meters. Okay, that is the length included between 3 points. My M3 is the moment at B. L2 is the same, 6 meters. And yung coefficient na idadagdag natin dito is due to the loads. So, in this case, yung load dito, that is uniformly distributive load, that will be, if you remember this formula. Okay, so hindi ko i-discuss further yung theory of structures dito. Okay, ang importante dito is yung analysis or the design of rectangular beam. Okay, so by this, I will substitute. Magiging ganito yan. Okay, now take note that MB can be calculated directly by cutting at this section. Okay, if I will cut at that section, that will be MB is negative 130.1 times the length times the moment arm, and that is negative. Okay, that is negative because as you can see, this will bend here downward pa ganyan. Okay, now I will substitute our B dito and lalabas ito, MA. Okay, so as you can see, we have the moment at A and the moment at B, but they are both negative. So we will calculate pa yung positive moment. Okay, so how can we do that? Okay, so medyo naglag. So ito yun, nag-gather natin yung MA and MB. Then I will draw first the moment diagram. Okay, that will be the moment diagram as a function of distance niya. Okay, now take note that we have the moment at A dito. Ayun. Okay, so at this point, initially we have 0, then it will have an abrupt change of moment downward. Okay, that is negative 455. Okay, so since at this point, if you can imagine, the bending will be ganito, meaning may positive moment dito, and it will look like that yung moment diagram natin. At this point, ito yung pinofocus natin dito na dapat nating makuha. Okay, in this point, yan yung moment at B, that is negative 260. Okay, and of course, babalik yan dyan. Okay, so our main objective here is to calculate this moment. Okay, so unang-una yung maiisip is dadaan tayo sa shear diagram. Okay, so here hindi ko gagawin yon. Okay, ang gagawin ko is ikakat ko lang to dito, then I will take that internal moment dyan. Yan yung moment at positive, maximum positive. Okay, so first I need to calculate the RB muna. Okay, so RB can be calculated by summation of moment at A. Okay, so by that will be W times 8 times the moment arm na 4. Then this RB will create counterclockwise moment, that will be RB times 6 meters. Okay, then this 455 will also create counterclockwise moment, so minus 455 equals 0. Okay, next we can calculate RB, that is the value. Now after that, again, I will cut this section dito to locate this or to calculate this maximum moment dito sa positive. So we need to locate this distance x dito. Okay, so how can we do that? Okay, so ganito yan. Ika-cut ko siya dyan. I will cut at this portion. Okay, ito yung matitira. And of course, when cutting the beam, may shear diagram, shear force tayo dyan, internal shear V. And ito yung moment na needed nating makuha. Okay? Now take note, at the maximum moment, shear is 0. Okay? That is why yung slope natin dito is 0 kasi. Okay? So anyways, nasa theory of structures to. Okay? So to calculate the value of x, just simply summation of forces vertical looking at this section. Okay? That will be RB minus 130, yung distance is 2 plus x, and shear V must be 0. Okay, so we have this one, 2.75. Now, after we got this value of x, okay, so I can take this moment na by just equating the moments here. Okay, so that will be the positive moment is 617.5 times x, 2.75, then minus the moment created by this uniformly distributive load at this section. Okay, that one. I hope you can follow that. 130, this distance here is 2 plus 2.75 or 4.75 times the moment arm equals to 0. And that positive moment here, ito yung gagamitin nating MU. Of course, this load here is factored load, meaning this moment na makukuha natin is factored load din. And of course, ito yung gagamitin natin to design that beam. Okay, so, take note pala, if a design problem is yung pinapahanap dito is the required steel area or the number of tension bar. Ganito yung design. Pag analysis problem or investigation, may binigay na siyang reinforcing bars. Okay? And we will just investigate the capacity pag ganun. But here, we are in design problem pa. Okay? So, pinapahanap yung bars. Okay, what's next? Okay, so I will just gather the moment. Okay, ito yung gagamitin natin. Okay, ito yung step 1. Natapos na natin yung step 1. Okay, what will be the next step? Okay, step 2. Hahanapin natin yung boundary moment in order that we can say that it is singly or if this will be designed or as doubly. Okay, yan yung magiging boundary moment natin. So, where can we find that? Okay, so remember, I presented to you at least 2 boundaries na possible na gagamitin ng examiner. Okay, this one, using epsilon t is greater than 0.004. Okay, this was discussed on our previous lecture. Okay, so using this as rho max. Okay, I will call this as rho max na lang dito. Okay, sa video natin last time, that was rho limit yung ginamit ko. Okay, gamitin na lang natin yung rho max. Okay, so 0.85 FC prime, okay, that one, and just simply substitute the values and we have this rho max. Okay, now take note, boundary moment yung kukunin natin. So kunin muna natin yung AS max. Of course, rho should be maximum, rho BD, that is the AS max. Then calculate natin yung C max. Okay, that formula. And of course, this 3/7 is dapat the same sila dito. Okay, as you remember, look at the first video na lang or just rewind para makita nyo saan to natin na-derive. And that one. Then after this, we will calculate the A or A max. That is one of the parameters sa moment arm natin. Okay, beta 1 C max and that one. Next, makukuha na natin yung MN max. Okay, that will be the value. MN max is ASFY or that is just the tension of the steel times ito. Kaya dumaan pa tayo dito para makuha natin yung A max sa moment arm. Okay, and the AS. So here, that should be AS max. Okay, since MN max yung kino-consider natin. Okay, next. Direct substitution. And we have this MN max. Okay. Now after this, take note that we will compare this to the factored moment. So we need to convert this into a design moment. Okay. Ito yung factored moment. Ito yung design moment from the beam talaga. Okay. So we need to multiply this by reduction factor. Okay. So take note that we are using strain as 0.004. Well, as you remember that the 0.004 is in the transition zone. So using that formula for phi in this transition zone, ito yon. Okay? I hope you remember this. Then take note that 0.004 na strain will correspond to the actual Fs as equals to 800 MPa. Okay? That will be 800 MPa. Multiply mo lang ng E na 200,000. Then substitute and ito yung gagamitin natin na reduction factor dito since ito yung boundary na ginamit natin. Okay? Now we can have the phi MN max or the design moment. Okay? The design maximum moment. That one. Okay? After this, ito yung i-compare natin sa factored moment. Okay? We just have finished this step 2. Ito yung step 2 natin. Okay? So, compare this to the factored moment or MU. So as we can see, our MU is lesser than the Vmn max. That means, kaya lang ng beam without the compression bar. Okay, pag lumagpas ito, meaning kailangan na ng tulong ng beam sa compression bar. Kaya magdoble na tayo at that time. Well, in this case, kayang-kaya ng beam alone. That will be singly reinforced. Okay? Okay, so next step, step 3, required steel area. Okay, if naging doble ito, hindi na siya katulad dito ng step natin, step number 3. Iba na siya. It will be different na. Okay? So, step number 3, required steel area. So, how can we calculate that? Okay, so, we will equate our factored moment to Vrn BD squared. Okay, so take note, we derive these formulas or pinakita natin. Okay, just substitute. And our reduction factor here should be that one. Since ito yung ginamit nating boundary. Okay, 0.004. Kung hindi itong reduction factor yung gagamitin natin dyan, hindi na siya magtutugma sa boundary natin. Okay? That one. Ito yung magiging reduction factor and we can calculate the Rn. Next, using this formula, okay, we derive this. We have that Rn. Okay, direct substitution and that will be that value. Okay? Now, actually, yung hinahanap sa number 2 is required steel ratio. So, it can be the answer. But, in the code, we should pass this criterion. Okay? Sinabi sa code, ES minimum shall be the greater of A and D. Okay? So, disregard muna yung statement dito sa ibaba because that is for T-beams. Okay? So, ito lang. So, kailan natin to gagamitin? Actually, sinabi lang niya, should be the greater of the two. But, para mas mapadali, gagamitin lang natin to if yung FC prime will exceed 31.36 MPa. So, dito yan. Ito gagamitin natin to if yung FC prime is lesser than 31.36. Dito yan kinuha. Okay, so we will just equate this one. Okay, tatanggalin natin to. Ito yung row. That one. Tatanggalin natin yung BWD. Okay, yung kinuha natin yung nakuha natin yung 31.36 is from this 0.25 the square root of FC prime. Okay, that is 0.25 square root of FC prime. No, that should be alpha. Okay, and alpha solve equals to equate natin dito. So that will be 1.4. Tatanggalin na lang natin yung FY since maka-cancel out man lang sila. Okay, then if we do shift solve, ayun, lalabas 31.36. Okay, ito yung limitation natin sa FC prime. Okay? Okay, so since our FC prime is lesser than 31.36, diretso na tayo gagamitin ito as the row minimum. Okay, so that one, 1.4 over Fy, and that is that value. Okay, well, as we can see, yung row or yung required steel ratio natin did not or hindi bumaba sa row minimum. Okay, in that case, meaning napasa natin itong code na to. We passed this code. Okay, so that one, and that should be the answer. Okay, well, in that case, if bumaba yung required steel ratio natin sa row minimum, ang gagamitin natin na row is the row minimum. Okay, so ito yung answer sa number 2. Now, next, we need to calculate the AS or the required steel area. That one in step 3. Okay, so AS is equals to row BD. Then, ang row natin, we calculated that already. Substitute and we have this AS. Then, to calculate the required number of tension bar, just equate areas. Okay, AS should be equals to the total number of cross-sectional area of the bar. So, take note that the bar is a circular polygon, no? Ang cross-section niya, that will be area of a circle. We have this diameter here. Then, i-multiply natin on how many bars. And from here, we have this AS substitute dito and we can calculate the n. Okay, 4.95. Of course, we will round this up. Hindi natin i-round down yan. Hindi yan spacing. Okay, round this up para mas maging safe talaga. That one. Okay, so this is just one common boundary. Okay, di ba sinabi ko, it can be, we can use any boundary that should be 0.004 until up. Hindi lang pwede bumaba yung epsilon t natin sa 0.004. Ito lang yung sinabi sa code. Hindi niya sinabi na limited lang tayo sa 0.004. Okay, so we will use another common boundary dito. Yung 0.005 na strain. Okay, that one. As you remember, ito will correspond the tension controlled. Okay, so I advise this to my student na ito yung gagamitin natin when we have exams. Okay, when we have quiz or exams, ito yung gagamitin nating boundary, 0.005. Okay, by using this boundary, we derive this formula. Okay, nag-iba lang dito, naging 3.8. Okay, so direct substitution and we have this rho t. Okay, tinawag ko siyang rho t, that is for transition controlled. Next, again, we will calculate the AST. Again, transition yan. And that will be that value. Next, kunin natin yung CT or C for transition limit. And that is 3.8. Okay, kung ano yung ratio dito, yan yung ratio dyan. 3.8D and that is that value. Then, kukunin ko yung 80 natin and that is that value. Okay, you can follow lang that. The same process kanina. Then, MNT or the nominal moment for transition limit. That one. Just substitute. And we have our MNT. Then, ano yun? Kukunin natin yung design. Multiply pa natin yan ng phi. And take note, since this is a tension controlled based on our boundary, that will be 0.9. Okay, then phi MNT, that is 263.79. Okay, and ito yung i-compare natin sa factored moment. Okay. That one. So, comparing this, para malaman natin if singly or doubly, okay, so as you can see, still yung MU natin is hindi lumagpas sa ating boundary moment for transition. Okay, so again, I will advise you na ito yung gagamitin natin na boundary, hindi yung isa. And to be clear, walang mali if gagamitin mo yung 0.004 or gagamitin natin yung 0.005. Both pasado sila sa code, but as far as I'm concerned, ito yung ginagamit ng ASEP sa Pilipinas. Okay? 0.005. Wala naman kasing magpapakahirap pag-design. Okay? At napakaliit lang yung range ng strain sa kanila. And dito, mas madali yung design dito. Okay? So, singly. Then, step 3, we'll calculate the required steel area. Again, the same process, RNBD squared. And, of course, yung phi natin dito magiging 0.9 na. And our Rn here is that value. Then, using this formula for rho, then, we can directly substitute the givens dito. And, again, calculating the rho minimum. Then, we will compare that. And as you can see again, that is greater than to the rho minimum, meaning na ipasa niya yung code sa minimum steel area. Okay? And ito yung answer sa number 2. Now, for number 3 again, calculating the AS, direct substitution, yan yun, 1669. So, as you can see, medyo nagbago na. Mas lumiit. And that one, equate natin yung number bars, and that is 4.39. And again, hindi natin yan i-round down. Dapat rounded up yung number bars. Again, N is 5. Now, as you can see, the same lang yung answer natin sa yung 0.004, di ba? Kaya, almost konti lang yung changes ng answer natin dito in design. Kumbaga, in terms of number of bars, almost the same lang talaga sila. Kaya, wag na tayong magpakahirap na gawin yon na 0.004. Well, in the purpose of illustrating lang, pinakita ko lang yon para ma-differentiate natin yung pinagkaiba. Okay?